observation, if it, you also wound up picking an action. Either you picked or you saw the other guy doing the action. Okay, and then based on that action, in particular, if you're doing it, you do an action based on the observations you got, you get a reward. Okay, and then underlying dynamical system has now gone to S1, and then you get, you don't know what the real state is, you only know what observation you got, which is Z1. Now obviously, these are not one-to-one. Many states can give the same observation with different probabilities. Okay, so when you get this observation, you don't know that you are in S1. You just know that this may be consistent with a whole bunch of states with different likelihoods. Okay, and then you wound up doing an action again, you get some reward, and so on. This is POMDP. So if for this 1 hour until your eyes come back to full non-blurriness, you cannot stop driving, right? You will still be driving. There are random number of people driving with these funny glasses that eye doctors give them, and they're just happily driving, and then they're seeing the world at some level, and they're making optimal actions with respect to the observations that they're getting. Once in a while they will get into accidents, but then people with full eyes also get into accidents. We don't really know, right? So the question, of course, is how do you select the actions? The actions are under your control. How do you select the actions such that your reward is maximized in the long term? Okay, this model is, the only difference between this model and MDP is this layer, Z0, Z1, Z2. Because the agent only gets to see this. If Z0 is equal to S0, Z1 equal to S1, then it's an MDP model. And in that case too, you start from a given state and you're trying to do a policy, which is, do a set of actions based on the state. You decide an action that will maximize your expected reward. And computing this policy of mapping between states to actions is what MDP was interested in doing. Okay, the first question that we have here is, what should the policy be here? The policy of the agent has to be, if I am getting this input, I should do this action. What should be the input? For MDP, it is, if I am in this state, do this action. For POMDP, what should it be? What?
An observation.
An observation. The question is it just the current observation? What? You have to look at the past. If you think about the guy who just left the ophthalmologist thing, right? And his car has a blind spot and he's also blind now. Normally cars already have blind spots, so there could be people in the blind spot lurking. And now, of course, so basically car driving is already partially observable, right? So I look like this. There's nobody there. Can I just optimally go into the next lane? I could be on part of one of those, I could suddenly be on top of one of those smart cars, which might be right in my blind spot. Right? And they won't look that smart anymore because they're now under my car. Okay. So the issue is that you cannot just, based on the immediate observation, you cannot assume you can go there. If you have been looking through your rear view mirror and you saw this funny looking smart car for the last 2-3 seconds, now you don't see anybody, but neither do you see a smart car in front of you, and you didn't pass by any exit. Is it okay to just change the lane? No. Your decision cannot be based on the current observation. It has to be based on what?
Previous observations.
How many previous observations? All of them. What goes off if I say decision is made not just about a property of the current state, but about a property of many states before? Markovian property. POMDPs are not Markovian if you think in terms of observation to action. You have to think in terms of history of observations to an action. History of observations to an action. Do you understand that? Okay? That's the first thing to learn. Let me just see. Okay, so a policy for PalmDP maps the history of observations to an action. Now, history of observations is too cumbersome to keep track of. Exactly how much are you supposed to keep track of? Okay, I can really tell you that in a partially observable world, you probably have to remember what was there yesterday while you are driving today. Because yesterday I saw people working on this road, there was a huge big hole, and today I can't, there is fog in front of me. I should put 2 and 2 together and say there may be a big hole in front of me right now. It was based on my yesterday's observation. In general, you have to keep track of your observations since you were born, or even before, really. Okay, so it's a very cumbersome thing to think in terms of mapping between history of observations to an action, which is what a PalmDP policy is. There are 2 ways of compressing the history of observations into a compact structure. Structure 1 is belief state. Okay, it turns out if you just keep track of your belief state, which is a point on this simplex, then in essence you don't need to remember what you have seen. Essentially the belief state itself completely specifies all the possible states you could be in and the probabilities associated with that. So it would have told you, based on the fact that yesterday you saw construction workers working there, and after all the actions you have done yesterday, today your belief state would say there is a non-zero probability that you are in a state where there is a big hole in front of you. So you basically took the history and compressed it into the belief state. Okay, now you can just say the policy is a mapping from belief state to action. That's Markovian. So although PalmDPs are not Markovian in the only input that the agent gets, only immediate input that the agent gets, which is the observation, because they have to keep track of the history of observations, they are Markovian in the space of belief states. Okay? And of course belief states are fully observable, it turns out. Because you are in the beginning, you know what your distribution is, and then after every action you can update the distribution. We'll talk about how to do it analytically. And so you'll always know what your belief state is. So not only is it Markovian, it's also fully observable. So a PalmDP is really an MDP in space of belief states. Looks like a great idea, except for the fact that the last time we looked at MDPs, we looked at discrete state spaces. Now we are looking at a state space which is the simplex. So there are infinite number of states, and you want to always compute value, right? V star. V star could be infinitely, squiggly, and you might need like infinite amount of space to just represent the value function. Okay, so the other thing that I was just about to say is, not here, let me see. Yeah, the 2 sources of PalmDP complexity. There is the quote-unquote curse of dimensionality, which is no big deal really, because MDPs also have the same problem. Curse of dimensionality is the more states, the harder the problem is. The more states, the harder the problem. As the number of states increase, PalmDP becomes harder. So does MDP become harder. In the case of PalmDP, it's particularly sad because as the number of states increases, the dimensions of the space of states increases, because each state is a separate axis. And the belief state is a point, it's a point on the simplex in this n-dimensional state space. So it really is a big deal, as the number of states increase for PalmDPs. But it's also kind of a big deal for MDPs. Yes, sir.
Would you please go back to the picture that you have shown? The graph of.
Okay, let me complete this, and then we'll
sure.
either do it under the class or next class. Okay. Okay. The other point that I want to make is, I'm just trying to get you to think about this while we come back to next class. So this is this. The second is the curse of memory. At least in the past at least, we basically had to represent the value function and the value to policy function. Both the value function and the policy function for us in PalmDP can be infinitely large. Because if I just say for each belief space you need wind up doing a different action, there are infinite number of belief states, you are sunk. And if you just say, oh, no, just give me the optimal value function, the optimal value function can be really crinkly on this simplex. You need some sort of piecewise smoothness. And what, to the extent we are completely sunk with PalmDPs, the reason people start celebrating a couple of things is it turns out for many cases, the value function would be piecewise linear and convex on this simplex. We'll talk about why that makes sense next class. It will be piecewise linear and convex. So it cannot be infinitely crinkly, at least for finite horizon case. For the infinite horizon case, it can be infinitely crinkly. Okay? The one other point I wanted to make is in terms of the policy, we can think in terms of belief states, which is what we will spend in the beginning for value iteration. The other thing you can do, basically remember the reason belief states were important was because you needed to compress the history of observations into one single data structure. Belief state is one. There is another way of remembering the history of observations. Don't put it in the state, put it in your plan. Don't say that the plan is just a direct mapping between something and an action. Say that my plan is a finite state, finite memory controller. Okay? Which takes the input, remembers the state it is in and decides what the action is. When I say the state, it's not the state of the world, which I don't know. It's the state of my plan. Okay? My plan can have three states. There is state 1, state 2, state 3. If I'm in state 1 and I get observation O1, I do action A1. If I get observation O1 when I'm in state 2, I'll do a different action. This would be a finite state controller with 3 states. So basically, the plan is counting where you are. So it's essentially taking the sequences of histories and splitting them into 3 equivalence classes because you have 3 states. In essence. So if you learn finite state controllers, that's one way of essentially handling this problem that the immediate input, you cannot make your decision based on the immediate input because you need to consider the sequence of states, a sequence of observations. So for the policy iteration, remember for MDPs there was a value iteration and a policy iteration. For the value iteration, it turns out it's better to think in terms of belief state representation. For the policy iteration, belief state representation is useless. Okay? And a finite state controller representation is much better. But then, who are we kidding? This is the slide that you can put next to your pillow and sleep tonight. Okay? Basically, computational complexity for PalmDP is for finite horizon, it's p-space hard. For finite horizon, it's p-space hard. But it's only NP complete if it is fully unobservable. This is what I meant by saying sometimes you are jealous of your blind friends. Right? I mean, you shouldn't be, but in some sense, the problems that you would not expect a non-seeing agent to be able to solve some of the problems at all. And so the fact that they didn't solve it doesn't mean they don't have a brain. Whereas you have eyes and you still don't solve the problem, I then say you have no brain. And normally it's a much bigger put down in human race to be told that you have no brain than to be told that you have no eyes. Right? Okay? And so it turns out that the conformant planning, conformant probabilistic planning is only NP complete for finite horizon. Whereas conditional probabilistic planning is p-space hard. A cheap way to remember why this is the case, because the horizon is constant, right? It's in class NP if there is a single plan, which is what this would be. If you can't sense, it will be a single line plan, and so it will be in the class NP. Okay? If you have observations, then you have basically the horizon becomes the depth, and I can pack this depth with a nice big binary tree, with each interior node being a separate sensing action. Now I have to consider, to say that this works, I have to consider each of them and say they all work. So it's no longer in class NP. It's a cheating way, it's not really a proof, okay? For infinite horizon, it's really nice, it's undecidable. I mean, all you logic people who had this superior attitude thinking we start with first order logic, which is already semi-decidable, so you guys are playing, toy games, what's the problem? Finally we are in the same level, because POMDP is just doing optimal actions in the atomic representation. With infinite horizon is undecidable. So if anybody tells you why can't you do anything optimally, you say, are you crazy? Because my life is at least a POMDP. If I assume, if I do not actually model any of you, then it's just a POMDP. If I model you, then it's a tech POMDP, decentralized POMDP, which is worse. Because you don't expect me to be doing optimal things. It's undecidable problem. Then you can talk about approximations. If you allow kind of epsilon approximation, it's NP hard. And if you also allow policies which are either memoryless or bounded memory, that means policies which have, remember I have a finite state controller. Suppose I say, find me the best policy among all policies that have at most 8 states in the finite state controller. That's like saying, find me the best 7th order polynomial that approximates this data. It may not be the case that this data is actually generated by a 7th order polynomial, but you're finding the closest 7th order polynomial that approximates this data. Similarly, I can fit a bounded memory controller to the optimal policy that I haven't yet computed. This is a great unholy combination of learning and inference together. That's one way you wind up doing it, but essentially it will again be NP hard because the number of policies you are looking at will be small. And so you just have to differentiate between them and see which is the best. All of them can be quite far from the optimal policy, which is probably requires 2 power 10 states in the internal representation of the plan. And we'll stop here. I'm really kept you too long today. But think about this distinction between the states of the plan and states of the world and the observations. And if you still, your brain isn't hurting, I'll see you on Wednesday.